In this video, we will be looking at section 8.3, which covers polar form of complex numbers. As a review from section 3.6, we're going to start by looking at imaginary numbers. So the most basic complex number is I, which we define I to be the square root of -1, and we call it an imaginary number. And then any real multiple of I is also an imaginary number. So something like 2i, 5i, -12i, those are all imaginary numbers. We're going to start working with imaginary numbers by simplifying some negative square roots. So first up we have the square root of -25. If we break that into the square root of -1 times the square root of +25, we see that this is I times 5, which we would write as 5i. Next up, we're looking at the square root of -18. I'm going to start it the same way as I started the last one. Write it as the square root of -1 times the square root of 18. We know that the square root of -1 is I, but we have to handle that square root of 18. So we have to remember how to break down radicals. I'm going to take 18 and break it down to its prime factors. 18 is 6 times 3, and 6 is 3 times 2. The 3's pair up, so they get to come out front. The 2 doesn't pair up, so it stays under the radical. So I get I times 3 times the square root of 2, which I would write as 3i times the square root of 2. So these are imaginary numbers, but we can combine imaginary numbers with real numbers, and that gives us complex numbers. A complex number is a number in the form z equals a plus bi, where a and b are real numbers. We call a the real part of the complex number, whereas b, or sometimes bi, is the imaginary part of the complex number, again where I is equal to the square root of -1. When we're working with complex numbers, we can do arithmetic on them, very similar to how we do with real numbers, or even with polynomials. So let's see if we can simplify each of these complex numbers in the arithmetic between them. So first up we have -2 minus 4i plus 1 plus 6i. I'm just going to combine like terms. The real parts are going to go together, and the imaginary parts are going to go together. So -2 plus 1 is -1. -4i plus 6i is +2i. So we're looking at -1 plus 2i. In the next one, we have 2 minus 3i minus 3 plus 2i. I'm going to have to distribute the negative to my second complex number, so let's get rid of all these parentheses. I have 2 minus 3i minus 3 minus 2i. Combining like terms, this is -1 minus 5i. Next up, I have 5 minus 2i times 3i. That 3i is going to have to get distributed. I know it's out back, but it's still multiplied by everything in those parentheses. 5 times 3i is 15i. -2i times +3i is a -6i squared. But I never want to see an I squared in your answer. I squared is equal to -1. So let's make that switch. We have 15i minus 6 times -1. Since 6 times -1 is +6, or sorry, -6 times -1 is +6. So this is 15i plus 6. But it's standard to write the real part first, the part without the I. So I'm going to rewrite this as 6 plus 15i. Next up, we're looking at -2 plus 4i times 8. I'm going to distribute my 8. That's going to give me a -16 plus 32i. Nothing else to that one. Then I have -1 plus 2i times -2 plus 3i. I'm going to FOIL this. -1 times -2 is +2. -1 times 3i is -3i. 2i times -2 is -4i. 2i times 3i is 6i squared. I'm going to combine my like terms. So I have 2 minus 7i plus 6 times negative 1. 6 times negative 1 is negative 6. So this is 2 minus 7i minus 6. And if I put my real parts together, 2 minus 6 is negative 4. And we still have our minus 7i. Finally, we have 3 plus 4i times 3 minus 4i. I'm going to FOIL that one as well. I'm going to get 9 minus 12i plus 12i minus 16i squared. That is 9. My 12i's cancel out because one's positive and one's negative. Minus 16, and I'm going to change my I squared to a negative 1. Negative 16 times negative 1 is positive 16. And 9 plus 16 is equal to 25. Now this last one is really important because we use this idea when it comes to dividing complex numbers, which we'll see on the next slide. When we're dividing complex numbers, it's really important for us to not have an I in the denominator. So we use this idea of multiplying by the same complex number, just with a different sign on the I term, so that we get a real number instead. This idea of having the opposite sign in front of the I, but everything else stays the same, it's called the complex conjugate. So as you can see, we're going to divide some complex numbers, and we don't want any i's left in the denominator. So we're going to multiply our numerator and denominator by the complex conjugate of the denominator. So first up, we're looking at 3 plus 4i over 2 minus I. I need to make sure that there's no I in the denominator, so I'm going to multiply by the complex conjugate of 2 minus I, which is 2 plus I. To make sure the fraction stays at the same value, I multiply by 2 plus I in my numerator as well. I'm going to have to FOIL my numerator and FOIL my denominator. That's going to give me 6 plus 3i plus 8i plus 4i squared. In my denominator, I'll have 4 plus 2i minus 2i minus I squared. Let's combine some like terms. I have 6 plus 11i plus 4 times negative 1. In my denominator, I have 4. The 2 i's cancel out, so minus a negative 1. That gives me 6 plus 11i minus 4 over 4 plus 1. And simplifying that, I'm left with 2 plus 11i over 5. Oops. Now we like it to be an a plus bi form, where the real part and the imaginary part are separate. So I'm just going to break up the fraction so that I have 2/5 plus 11/5 I. That way we have our a value of 2/5, our b value of 11/5, with the I out back. Let's try another one with this 2 minus 5i over 6 plus 7i. Again, I need to multiply by the complex conjugate of the denominator. That's going to be 6 minus 7i, and I'm going to multiply it in my numerator and denominator. Yay, more FOILing! 2 times 6 is 12, minus 14i, minus 30i, plus 35i squared. In the denominator, I'm looking at 36 minus 42i plus 42i minus 49i squared. That's going to give me 12 minus 44i plus 35 times a negative 1 over 36. The 42i's cancel out, and then minus 49 times negative 1. That would be 12 minus 44i minus 35 over 36 plus 49. Finally giving me negative 23 minus 44i over 85. Splitting up my two fractions, that's a negative 23 over 85 minus 44 over 85i. All right, just one more. We're looking at 1 plus 2i over 3i. Now, it might not be obvious what the complex conjugate is, but if the denominator is 3i, that's the same as 0 plus 3i. So the complex conjugate is going to be 0 minus 3i, which is the same as just a negative 3i. So I'm going to multiply a negative 3i in my numerator and denominator. Distributing gives me negative 3i minus 6i squared over a negative 9i squared. So that's negative 3i minus 6 times negative 1 over negative 9 times negative 1, negative 3i plus 6 over positive 9, but we put the real part first. So this is 6 minus 3i over 9. If I break that up, that's 6 ninths minus 3 ninths I, and those reduce. So I'm looking at 2/3 minus 1/3 I. All right, now that we've practiced some arithmetic with these complex numbers, let's see what we can do with them visually. So what we're going to do first is we are going to plot complex numbers. Plotting complex numbers on the complex plane is very similar to plotting points on the Cartesian coordinate plane. However, what makes plotting these complex numbers different is actually our axes. Instead of having what we call an x and a y axis, we have a real axis and an imaginary axis. So you can see this number plotted here is 3 plus 2i. You find 3 on the real axis, 2 on the imaginary axis, and where they meet is 3 plus 2i. It's similar to plotting real numbers, Cartesian coordinates, because we have an x value of 3 and a y value of 2, if we want to think of it that way. So if I want to plot 4 minus 2i on the complex plane, it will be a lot like plotting 4, negative 2. So I find 4 on my real axis, go down 2 on my imaginary axis, and I get that point. Negative 3 plus 5i will be negative 3 on the real axis, 5 on the imaginary axis. Next up, we have negative 2. I'm going to write it as negative 2 plus 0i. That way I can see what my imaginary value is going to be. So I'm at negative 2 on the real axis, 0 on the imaginary axis. So that actually puts me on the real axis itself. Next up, I have 4i, which I can think of as 0 plus 4i. So I'll be at 0 on my real axis, but 4 on my imaginary axis. Finally, I have 4 plus 6i, so I'll go to 4 on the real axis and 6 on the imaginary axis. Next, we are going to look at complex numbers in a different form, and that's going to be polar form. So the polar form of a complex number is z equals r cosine theta plus I r sine theta. That looks scary, but r cosine theta, that's the same as x. R sine theta, that's the same as y. So kind of like how when we just graphed, the x value came from the real part and the y value came from the imaginary part, that stuff is still following us here. An alternate form to write these complex numbers is z is equal to re to the I theta. These z's out front, that's just the variable we typically use to represent complex numbers. We call them z. So that part is just a notation thing. This re to the I theta is going to be important. Euler's formula states that this re to the I theta is equal to this other form, r cosine theta plus I r sine theta. What we're going to do for converting from this polar form to the form that Euler's formula has us working with, it's going to be really similar to some stuff we've done in the past. So let's see what we can do with it. We're going to write each of the following numbers in the form RE to the I theta. And I'm going to grab a blank sheet of paper just to make sure I have enough room. The first complex number we're going to work with is 6. And I'm going to write it as 6 plus 0i. That way I can see both parts. And my goal is to get to RE to the I theta. Well, if we think back to some of the formulas that we've used in the past, we know that x squared plus y squared is equal to r squared. So I can use this to help me find the r. The x value in this, or at least what we're thinking of as x, is 6. So we get 6 squared plus the y, or what we think of as y, is 0. So we have 6 squared plus 0 squared is equal to r squared. So 36 is equal to r squared, and r is equal to 6. No big surprise there. The complex number 6 plus 0i is 6 units from the origin. Not too much of a surprise there. Now we need theta. To find theta, we can either use the fact that cosine is x over r, or the fact that sine is y over r. I feel like using sine, but you can use either one. The sine of theta is equal to y over r, so that will be 0 over 6, which is 0. So the sine value is 0. If we looked at cosine, we would have the cosine of theta is equal to the x value 6 over the r value 6, which is 1. Both of these lead us to the same place, and there's only one place where sine is 0 and cosine is 1. That's at the angle 0. Hypothetically, we could use 2 pi, but it's more standard to use 0 since it's smaller. So if I want to write this in RE to the I theta form, that will be 6e to the I times 0, which is 6e to the 0. E to the 0 is just 1. So this is just 6. The number 6, written in the other form, is just 6. And you might be saying to yourself, well, that's silly. It might seem silly, but let's try another one so that we can see how this looks when we have both a real value and an imaginary value. So next we're going to look at negative 3 plus 3i. We're going to follow the exact same steps. So first up, x squared plus y squared is equal to r squared. So we get negative 3 squared plus positive 3 squared is equal to r squared. 9 plus 9 is r squared, so r squared is 18, meaning r is equal to the square root of 18, which we've already simplified in this section. So I'm just going to remember that that is 3 times the square root of 2. Now before I start diving in on theta, I want you to think about what quadrant is negative 3 plus 3i in. It has a negative x value and a positive y value. That puts us in quadrant 2. So whether I use sine or cosine, I need to make sure that I'm coming up with a value in quadrant 2. I'm going to use sine and just see what happens. The sine of theta is equal to 3 over 3 times the square root of 2, which is 1 over the square root of 2. Well, 1 over the square root of 2, we don't like leaving square roots in the denominator, so I'll multiply by square root of 2 over square root of 2. That gives me square root of 2 over 2. What that boils down to is the sine of my angle is square root of 2 over 2. Well, wait a minute, that's on my unit circle. But I have to be careful. I need the answer in quadrant 2, where is sine, which is the y value, equal to square root of 2 over 2? Right here, 3 pi over 4. So my theta, whoops, wrong side, we'll try it anyway, is equal to 3 pi over 4. So if I write this in re to the I theta form, I have r, which is 3 times the square root of 2, e raised to the I times 3 pi over 4. I'm just going to write my 3 pi over 4 first. So this is 3 times the square root of 2, e to the 3 pi over 4i. We're going to look at one more. We're going to look at 2 minus 4i. And this one's not going to land on our unit circle, so we'll get some practice with the calculator. So we have x squared plus y squared equals r squared. So that's 2 squared plus negative 4 squared is equal to r squared. That is 4 plus 16 is equal to r squared. So r squared is 20, meaning r is the square root of 20. Let's break down 20 to make sure we don't miss anything. I'll do it over here. 20 is 4 times 5, and 4 is 2 times 2. So I can pull a 2 out front because those paired up, and a 5 stays underneath because it didn't pair up. So our r value is 2 times the square root of 5. Now I need to find my theta. First I'm going to think about what quadrant it is in. I have a positive x value and a negative y value. That puts me in quadrant 4. So I need to make sure whatever answer I get, it goes into quadrant 4. I'll go ahead and use sine because that's what I've been using. The sine of theta is equal to the y value, negative 4, over the r value, 2 times the square root of 5. That's not going to end up anywhere on my unit circle. I know that because there's a square root of 5 in it, and we don't have that anywhere on the unit circle. We've been dealing with radians, so make sure you're in radian mode. And I'm going to take the inverse sine of negative 4 divided by 2 times the square root of 5. That gives me theta is equal to negative 1.1071, which is in quadrant 4 because it's a negative angle, but it's not pi over 2 much negative. That's hard to explain. Pi over 2 is 1.57. We're not going a full pi over 2 in the negative direction, so we are in that quadrant 4. The problem is my open math really likes it if your answer is between 0 and 2 pi, and this is negative. I don't want a negative answer. I want to end up at the same place as this, but I want it to be positive. To end up in the same place, I need to rotate 360 degrees, which is 2 pi radians. So if I add 2 pi to this, it puts me in the same spot on the circle. It just has a positive value for theta. So that's 5.1760. So if I write this in re to the I theta form, I get 2 times the square root of 5, e to the I times theta, I'll put the I last, so 5.1760 I. And that's the form we're looking for. Now you might be wondering how this form can even be useful. Why would we have it? And think about some of the math we've done in the past. We added, subtracted, multiplied, and divided complex numbers. Well, what if we wanted to take complex numbers and raise them to a power? Not just square them, because then we can just FOIL it out, but like the 8th power, we would have to FOIL over and over and over and over. It would take forever. So we can use this form to help us raise this to a power, because in the form we were just using, it's a lot easier to raise something to a power. However, instead of using Euler's formula and using the form we were just doing, we're going to use someone else's formula. It's called de Moivre's theorem. It says if z is equal to r cosine of theta plus I sine of theta, then for any integer n, z to the n power is equal to r to the n power times the cosine of n theta plus I sine of n theta. I will tell you that this is on your formula sheet, but just like I did in the PowerPoint, I forgot to put it in the formula here. So make sure there's an n before your theta. So let's see what we can do with this. First up, we want to work with 2 plus 2i raised to the 8th power. It looks like I'm still going to need to know r and theta, so I can start by finding those. The other thing I need is n, but n is just my exponent, and that's quite clearly 8. So we know n is going to equal to 8. I need to find my r and my theta. And this is not wanting to focus. Let's try it anyway. X squared plus y squared is r squared. So that's 2 squared plus 2 squared equals r squared. 2 squared is 4, and 4 plus 4 is 8. So r squared is equal to 8. That means r is the square root of 8, which is 2 times the square root of 2. We have r, now we need theta. Remember that theta comes from using either sine or cosine. First, we need to think about what quadrant are we in. If x and y are both positive, we are in quadrant 1. Yay! You can use either sine or cosine. We'll get to the same place. The sine of theta would be equal to 2 over 2 times the square root of 2. Lots of 2's going on in this problem. The 2's cancel out, leaving me with 1 over the square root of 2. We saw earlier, if we multiply by the square root of 2 in the numerator and denominator, that gives us the square root of 2 over 2. That lies on our unit circle, the place in quadrant 1 where the sine of theta is equal to the square root of 2 over 2 is when theta is equal to pi over 4. So let's see if we can put this all together with this lovely theorem. So 2 plus 2i raised to the 8th power is equal to r raised to the n power. So that's 2 times the square root of 2 raised to the 8th times the quantity of the cosine of n, that's the 8, times theta, which is pi over 4, plus I times the sine of n, which is 8, times theta, which is pi over 4. All right, let's see if my calculator can do 2 times the square root of 2 raised to the 8th power. 2 square root of 2 raised to the 8th. That's 4,096. In parentheses, I'll have the cosine of 8 times pi over 4 is 8 pi over 4, which reduces to 2 pi, plus I times the sine of 2 pi. Those are unit circle values, so I can find those. The cosine of 2 pi is 1, plus I times the sine of 2 pi is 0. So this is 4096 times 1 plus 0, which is just 1. This is just 4096. So 2 plus 2i raised to the 8th power is equal to 4,096. Don't worry, they don't always come out that nice, so let's do one where things don't quite cancel out the way we want. It's not all unit circle stuff. Let's see what we got. So the next one we want to write or calculate is the square root of -4 minus 4i. This theorem is focused on raising complex numbers to powers. So first we have to think about how do we raise a square root to a power? Or sorry, how do we write a square root as a power? A square root is the same as raising it to the 1/2 power. So this is -4 minus 4i raised to the 1/2 power. Now we can follow all the same steps we did in the last one. We need to find r, we need to find theta. So let's start with r. X squared plus y squared is equal to r squared. This time we have -4 squared plus -4 squared is equal to r squared. 16 plus 16 is 32. So r squared is 32. So r will be the square root of 32, which I bet breaks down. 32 is 16 times 2. Sixteen is 4 times 4, and that's enough to where I have a pair of 4s, so they can come out front. The 2 doesn't pair up, so it stays underneath. So our r value is 4 times the square root of 2. Now let's go for theta. We have a -x and a -y value, so that's going to put us in quadrant 3. I've been using sine, so I'll stick with sine. The sine of theta is equal to -4 over the r value, 4 times the square root of 2. The 4's cancel, leaving me with -1 over the square root of 2. You're probably sick of me showing you that 1 over the square root of 2 is equal to the square root of 2 over 2. This time we just have a negative out front. So the sine of theta is equal to negative square root of 2 over 2. That actually does fall on our unit circle. The place in quadrant 3 that has a sine value of negative square root of 2 over 2 is 5 pi over 4. All right, so let's see if we can put it all together. So we have -4 minus 4i raised to the 1/2 power is going to be equal to, first we have r raised to the n power. So that will be 4 square root of 2 to the 1/2 times the quantity of the cosine of n, that's our power, 1/2, times theta, which is 5 pi over 4, plus I times the sine of n, which is 1/2 times theta, 5 pi over 4. So now we're going to simplify all this. Going to be a lot of calculator work here. So we have 4 times the square root of 2 raised to the 1/2 power. That's going to be about 2.3784. First up, I have the cosine of 1/2 times 5 pi over 4. That's 5 pi over 8. The cosine of 5 pi over 8 is negative 0.3827 plus I times, we have the sine of 5 pi over 8, which is I have I times this value, so I'm going to write the value first. 0.9239i. Now I can distribute through the parentheses. 2.3784 times negative 0.3827 gives me negative 0.9102 plus 2.3784 times 0.9239 gives me 2.1974i. That's what I'm looking for.